Hello everyone, welcome to my presentation for MLMI2020. I'm Yutong from University of Western Brittany. My research is also corresponding to the activities of Laboratory La Team, which belongs to the INSERM institution of France. Today I have great pleasure in introducing my paper, Multitasking Siamese Networks for Breast Mass Detection using Dual-View Mammogram Matching. Breast cancer has become a common disease that threatens women's physical and mental health. Over the past few years, the massive screening has allowed earlier diagnosis and better cancer management, so the survival improved significantly. However, the proportion of women recalled for further examination after screening remains very high due to the non-systematic double rating, which means that the number of radiologists is far from enough to realize second reading of screenings, resulting in a high recall problem. About 100 over 1,000 women screened or recalled for additional tests and unnecessary treatments, while only about 5 are truly affected. In this context, computer-aided diagnosis system for mammography has been introduced to provide an objective view to radiologists. But conventional CAD systems are usually inefficient and not automatic enough to significantly improve diagnosis performance. It still needs further improvement to act as a second reader. In this work, we study low-dose X-ray mammograms. Mammograms are 2D projections of volumetric information. Among diverse types of breast abnormalities, breast masses are the most important clinical symptoms of breast cancer, and they have various sizes, shapes, textures, and contours in different cases. In addition, the contrast between mass and surrounding tissues are not obvious. All these features make mass detection very challenging. We have used two public databases. The first one is the InBreast, which consists of 410 mammograms, but only 107 images contain masses, which is a quite small database. The biggest advantage of InBreast is that it has very precise annotations of mass. Another dataset is the DDSM-CBIS. It's much larger, but it provides only coarse delineation of mass. There are mainly two acquisition viewpoints for each laterality, the view craniocaudal and the view mediolateral-oblique. Essential to make decisions in clinical routine, the information presented in the two paired CC-MLO views is highly complementary and could serve as a second source of decision. Indeed, the concept of multi-view information fusion was recently introduced to improve detection and classification of pathological images, thus helping radiologists to reduce the rate of false detections. In this context, we want to take advantage of the information from the CC and MLO views in order to improve the performance of mass detection and localization. However, due to breast deformation, different acquisition conditions, and the lack of 3D information, registration of the entire mammogram is difficult. Therefore, multi-view fusion is a challenging task. In this case, we start with matching at the level of mass regions, such as the two mass patches shown on the left, which are from different views but containing the same mass. Patch-based image matching has been extensively used in computer vision. The Siamese deep neural network model is highly used, which includes two identical subnetworks with shared widths, such that features from two different input images can be extracted simultaneously. On this basis, we can exploit the correspondences between masses from the CC and MLO views. The Siamese network consists of a feature network, in which two fully convolutional networks with shared widths are employed for feature extraction, shown by A in the figure, and the matrix network B is used to exploit the potential relation between the viewpoints. The two branches take patches from CC and MLO views separately, and each branch of the feature network takes both positive and negative patch samples. that is to say with or without mass, as input, to calculate the features. The feature vectors f1 and f2 are then concatenated and fed into the matrix network B for a patch comparison. The matrix network can be a fully connected network composed of several fully connected layers and softmax layers trained with a cross-entropy loss. Alternatively, we can instead employ a contrastive loss, which is typically exploited with Siamese networks to learn paired data relationships. The contrastive loss optimizes the mass matching task by manipulating the distance between the pairs in feature space. Then, we proposed a multitasking Siamese model towards simultaneous patch-level matching and classification. That is to say, we take as input candidates from two views, and we provide as output both mass-non-mass classification and mass matching results. Apart from the matching network, we incorporate into the pipeline two branches for CC-MLO mass classification purposes. Each of these branches has its own fully connected layers. We not only jointly learn representations from the two views, but also jointly learn two tasks. Multitasking learning has many advantages, such as reducing processing time and computing resources, as well as improving robustness by extracting generic features. The network parameters are updated through the optimization of a combined loss function. The designed loss is the sum of three losses. In this way, we can not only process the correspondence and classification of masses at the same time, but also improve the performance of each of these two tasks. In order to have a complete and automated CAD system, we have proposed a full detection pipeline that takes CC-MLO image pairs as inputs and which provides precise mass detections as well as correspondences between dual-view masses as outputs. The selection of candidate patches is based on YOLO V3. We use it as a pre-detection model of masses from high-resolution mammograms. These candidate samples are then fed into the combined network. Our multi-view and multitasking framework further eliminates false detections and discovers the latent relation between CC and MLO views. Our multitasking approach has been tested with several classic and effective models. Firstly, we show the results of multitask learning versus classification only. This part of the experiments is to prove the effectiveness of multitask learning. In most cases, multitasking models that combine classification and matching are better than classification-only scheme from 2% to 4% in accuracy, which reflects the benefits of dual-view matching. We obtain slight gains with the contrastive loss compared to cross-entropy, except for ResNet 101. The difference between networks is not obvious, demonstrating that deeper networks are not necessarily required in our case. Experiments through a full detection pipeline have given promising results and further prove the effectiveness of our method. Finally, I want to show the visual results for an example of a CC-MLO image pair. The three columns represent from left to right the pre-detection by YOLO, YOLO followed by a classification-only model, and YOLO followed by the proposed combined model. In this image pair, the number of false positive detections decreased from 7 to 1 from A to B, and further decreased to 0 without any false negatives. Additionally, the combined model C also successfully identifies the matching patches in both views, which can provide clinicians with reference to further rule out false positives that are difficult to detect. In conclusion, in this paper, we propose a unified Siamese network that combines classification and dual-view mass matching to take advantage of multi-view information. We prove the effectiveness of integrating multi-view information within the breast mass detection pipeline by extensive experiments on public datasets. Based on Siamese networks, our method generalizes well using different deep networks and shows impressive results as an integrated, computer-aided diagnosis systems. That's all my presentation. Thank you for your attention.